This is part 2 of the lecture on free fall. In part 1 of the lecture, I went through Galileo's experimental procedure that he performed in discovering acceleration due to gravity. That is, all objects fall with the same constant acceleration of 9.8 meters per second squared in the absence of air resistance. This situation is known as free fall. Because this is a type of motion involving one-dimensional motion with constant acceleration, this then means that the kinematics equations that we developed earlier in this unit can be applied to this all-important situation in describing an object in free fall. That's what we want to do here. We want to describe those equations. Okay, because this is one-dimensional motion with constant acceleration, it's the same kinematics equations that are now used to describe free fall as we used earlier to describe what happens when rocket ships accelerate, cars slow down, and so on and so forth. However, we do rename things slightly. Earlier, when we were talking about such situations, we thought of it as occurring horizontally, which we then think of as the x direction. Here, this is a vertical type of motion, so then therefore we use the y direction instead. This then means that we begin to rewrite the position equation and the velocity equation in the following way. Okay, first of all, the position equation. The position equation is now written out in the following manner. Here's what the various symbols mean. We use the position as y instead of x. We have an initial value and a final value. And then the initial velocity in the y direction is now referred to as vy naught. And then we have the acceleration. The acceleration is g, downwards at 9.8 meters per second squared, and notice the value here is negative. By definition, for simplicity, we assume that the positive direction is upwards and the downwards direction is negative. Okay, and then the velocity equation. The velocity equation looks like the following. Once again, it's the same equation as before, but now just renamed slightly for this situation involving free fall. We have the final velocity, now referred to as v sub y, the initial velocity, once again referred to as vy naught, and then the acceleration downwards at 9.8 meters per second squared. If you algebraically combine these two equations together, you then end up with the third kinematics equation. The third kinematics equation is written in the following way. Like so. Compare the third kinematics equation here in its free fall form to what you saw earlier when talking about horizontal situations, that is earlier in this unit. However, when it comes to example problems, typically what I do is I concentrate on just the first two expressions because those expressions illustrate all of the basic physics more clearly than this expression does here. You are welcome, however, to use this expression when it comes to example problems and also exam questions, but I exclusively just use the first two equations to describe various situations. All right, now before we start to do examples associated with these expressions, the first thing to do beforehand, however, is graph them out. Understand the graphs of position, velocity, and also acceleration as functions of time for situations involving free fall. There are three situations for us to look at. An object, very simply, that is dropped from rest, an object that is thrown downwards, and then lastly, an object that is thrown upwards. Let's begin with an object dropped from rest. So graphs, and then first of all, an object dropped from rest. In all three of the scenarios that we'll look at, however, assuming that there is no air resistance, the acceleration is always the same value, a constant g downwards at 9.8 meters per second squared. So then therefore the acceleration as a function of time graph is always going to look the same for an object in free fall. Very simply, it just looks like this. So here's acceleration as a function of time. Right here is the value of g downwards at 9.8 meters per second squared, and then we have a constant acceleration like so for an object in free fall. Doesn't matter if the object is dropped from rest, thrown downwards, or initially thrown upwards. But now let's take a look at the velocity and position graphs for the three situations or scenarios. Okay, now for an object dropped from rest, let's immediately note that the initial velocity vy naught is equal to 0. And then therefore, if I graph out velocity as a function of time, I then have the following expression, or the following graph, that is. So when I graph velocity as a function of time, the y-intercept is 0, and then the slope of the line is just simply negative g. So then therefore I end up with a graph that looks like this. So the slope is negative g, and then right here is the y-intercept, the initial velocity of 0. Okay, then graph out position as a function of time. When graphing out position as a function of time for an object dropped from rest, we're graphing this expression here, which is a quadratic. So it's a parabola that opens downwards. It's always the same parabola for an object in free fall. The only thing that changes from situation to situation is the location of the vertex. If we drop the object from the origin, so we'll immediately set y0 equal to 0, and we drop the object from rest, these two terms here are equal to 0, and then therefore you end up with a parabola very simply that looks like this. Where right here at the origin is the vertex. And then you can easily visualize this in the following way. Recall that on a position as a function of time graph, the slope of the line tangent to the curve, that is, the derivative, is the velocity. So right here at the vertex, the slope of the tangent line is equal to 0. That's the initial velocity equal to 0. And then as the object falls downwards, then the velocity in the negative direction increases in magnitude, like so. So understanding these two graphs for an object that is dropped from rest is rather straightforward. They're also rather straightforward for an object that is thrown downwards. Okay, now for an object that is thrown downwards, the initial velocity is a negative number. Remember that we tend to think of the downwards direction as negative and the upwards direction as positive. So if I take an object and I throw it downwards like so, I give it an initial velocity in the negative direction. The only thing that changes then, therefore, on the velocity graph, as opposed to what I had earlier up on the top board, is the location of the y-intercept. Now the y-intercept is a negative number. Therefore, the velocity as a function of time graph just simply looks like this. So velocity as a function of time, it's the same line as before, that is like so, with a slope of minus g. But right here is the y-intercept, a negative number like so. So the object just simply speeds up in the negative direction. When you graph out the position as a function of time for an object that is thrown downwards, it's still the same parabola as before. That is the parabola that opens downwards, but now the vertex is no longer at the origin. Instead, the graph looks something like this. Like so, where right here is not the vertex. And once again, we can easily visualize why that has to be by picturing the derivative. So on a position versus time graph, the slope of the tangent line is the velocity. So right here at times t is equal to 0, notice that the slope of the ruler's edge is a negative number. That's this negative initial velocity right here, and then the velocity gets increasingly more and more negative as the object falls. Once again, these two scenarios here are relatively straightforward. The scenario, however, where an object is initially thrown upwards, well, that usually trips up introductory students. So once again, let me go ahead and clear up some confusion that you may have had about free fall prior to these lectures. All right, so let me do a little bit of erasing here. Like so. Okay, now this is the third situation for the object thrown upwards. For the object thrown upwards, the initial velocity Vy0 is a positive number. Therefore, if you graph out the velocity as a function of time, you're going to end up with the exact same line as before. Once again, it's a slope with a slope rather of negative g, but in this case, the y-intercept is a positive value for the initial velocity. That then looks like this. Like so. So right here is the initial velocity. The slope is once again equal to minus g. And then here's what's happening in this situation. On this portion of the graph, the object is moving upwards and slowing down as it does. And then right here at this instant in time, the velocity is at 0. And then it falls downwards in a negative direction like so and speeds up as it does. The entire time, however, the acceleration is a constant value of 9.8 meters per second squared downwards. Okay, now when I take my marker and the marker reaches its maximum height, that corresponds to this instant in time, how long is the marker at its maximum height? For literally an instant, a non-measurable amount of time. Imagine what this graph would look like if the marker, when it was at its maximum height, was there for a measurable amount of time. That would then look something like this. So the object would be moving upwards and slowing down as it does. It then reaches its maximum height with a velocity of 0, and then just all by itself, it decides to stay there for a while. And then it eventually falls down in a negative direction, like so. This is, of course, not what happens. Instead, the object reaches its maximum height, and it is there for literally an instant in time, a non-measurable amount of time. Okay, and then lastly here, for this scenario involving the object initially thrown upwards, we just sketch out the graph of the position as a function of time. It's the same parabola as the preceding graphs describing position as a function of time, but now we then have a new location for the vertex. In this case, the location of the vertex is in the first quadrant on that graph. So position as a function of time, same parabola as before, and now the vertex is here in the first quadrant. Once again, you could picture why this is in terms of the derivative. So right here, times t is equal to 0 on this position as a function of time graph. The slope of the tangent line there, the velocity is a positive number. That's this positive value here of Vy naught. And then the velocity goes from that positive value to a value of 0 here at this instant when the object reaches its maximum height. That's this point right here. And then the velocity goes from 0 and gets increasingly more and more negative as the object then moves downwards like so, speeding up as it does. So those are the sketches of the graphs associated with those situations for free fall kinematics. I'll conclude part 2 here. When I eventually move on to part 3, that's when we start to take a look at all important examples.